Hello everyone, welcome to my YouTube channel. Today I am going to upload another very interesting and informative video lecture related to simulation of perovskite solar cells on SCAP 1D. In my today's lecture, I will talk about a Nyquist plot, and I will talk about how we can compute a Nyquist plot against a set of range of input AC signal frequencies. And in today's lecture, I will explain that in SCAP 1D, how we can compute Nyquist plot related for perovskite solar cell simulation on SCAP 1D. So before starting off my today's video lecture, I would like to recommend all of you that kindly subscribe my channel. If you are new on my channel, kindly subscribe it so that you can get my all the latest videos on the time. So before the start of my today's video tutorial, I would like to share screen with all of you and so that I can start my today's computation and today's analysis about Nyquist plot, how we can plot Nyquist plot in SCAPs 1D related to perovskite or solar cells. So I'm going to share my screen with all of you. Okay, friends, first of all, before the start of today's lecture, I will try to explain a little bit introduction related to Nyquist plot and Nyquist criteria, how we can compute Nyquist plot and Nyquist simulation graphical representation scaffolding. One person should remember about a few things about that before the start of this plotation graphical representation. Let me suppose that I'm going to explain the Nyquist plot and Nyquist criteria and Nyquist explanation related to perovskite solar cells. Before that, we must know about technology named as EIS, very important, particularly used for perovskite solar cells. Basically, EIS is a technique named as electrochemical impedance spectroscopy. And this technique is basically used in order to check the effect of impedance responses of samples against a wide frequency range. So we can say that in order to compute effect of input applied AC frequency signal on our perovskite device impedance, we need a technique, and that technique is specifically called EIS, or electrochemical impedance spectroscopy. And for our kind of information, this technique is widely used, and normally the range of set of frequency is being from 1 hertz to 1 megahertz, so that we can check the effect of a different range of frequency over impedance of our perovskite that is being simulated in SCAP 1D. So I can say that EIS technology and technique is very helpful in computation of effect of input AC signal on my device impedance. And when we are talking about the Nyquist plot, remember that there are two kinds of impedances that need to be computed. First is basically the imaginary part of the impedance, and second is basically the real part of the impedance. I will show you and I will explain you on what axis we will take imaginary part and on what axis we will take on real part. So EIS technique or technology is basically used to check the effect of different range of frequency on impedance of perovskite device. And in order to compute data, or in order to extract data from EIS, normally we need some graphical representation in SCAPs 1D, like I just explained that Nyquist plot. So Nyquist plotting and Nyquist graphical representation is one of the most important methodology that can be used in order to extract EIS data commonly, and we can vary the input signal from a set of range of frequency, and we can compute its effect on impedance of our perovskite device. So I just explain one important thing, what is EIS, and I just explain that how we can compute the data, how we can extract EIS data, by which technique Nyquist plot. So I'm going to start my Nyquist plotation and the graphical representation, and I'm going to set my frequency, and then I can explain more important things, how the input frequency can affect on the impedance of our device on real part or imaginary part, how we can plot a real impedance and we can say that imaginary impedance on graphical representation, and what is the effect of the applied input signal or frequency signal, higher signal or lower signal on impedance of my perovskite device. So first of all, we need to mark this button. Okay. First of all, we need to mark this button, IV characteristic curve. And now we must know that from which analysis we can compute the Nyquist plotation. So we need to click CF, frequency and capacitance response. From that analysis, we can clearly compute the Nyquist plotation. And then we need to click over the illumination from dark to light. Okay. So next thing is that we need to change our V2 value. I'm going to set my V2 value 1.5, and I just click buttons stopped after VOC, so that my computation can be stopped on a certain range of applied voltage. Like if I'm getting my VOC value in 0.8, my computation is being stopped, or 0.9 and etc. But I have just kept a little bit higher value rather than that of my VOC value. Now, next, I'm going to change my input frequency range. I have just explained that normally EIS analysis or Nyquist plotation is being computed on the frequency range of 1 Hz to 1 megahertz. You can also vary the frequency range, some certain ranges, but normally we have seen that whenever we are trying to compute EIS analysis or Nyquist plotation in SCAP 1D, so we need to set a nominal range of input frequency, and I have just explained that a nominal range and commonly used range is between 1 Hz to 1 megahertz. So I'm going to set my input frequency 1 Hz to 1 megahertz. Okay, 1 raised power 6. Okay, now I have kept my input frequency range from lower range to higher range, from 1 hertz to 1 megahertz, and I'm trying to check the effect of this input AC signal on impedance of my device. I have just explained that there will be two kinds of impedances, like real and imaginary, and I will explain what kind of frequency can affect on my real impedance or imaginary impedance. I would like to explain what is impedance. Impedance is collective resistance either on your input side, either your output side. When we talk about the impedance, it is the collective resistance and denoted by Z, capital Z. So I just put my input frequency range from 1 Hz to 1 megahertz. I just click on capacitance frequency graph, because I know that Nyquist plotation can be only computed in response of frequency with respect to capacitance. I have already explained a detailed lecture about CEF analysis and CV analysis. You can watch if you don't know about what is CV analysis and what is CF analysis. But today's lecture is basically focused on Nyquist plotation and how we can plot Nyquist graphical representation in SCAPs 1D. So I just put it my first step, that is about the initialization of input frequency AC signal from a range of 1 Hz to 1 megahertz. Okay, next I'm going to start my computation. I'm going to start my simulation. I need to click over calculate single shot. We need to wait while the computation is being carried out. Then I can conclude what is the effect of lower input frequency and higher input frequency. Okay, my computation has been completed. Now I need to show you what kind of relationship and graphical representation we are getting from CF analysis. Okay, here you can see that we have almost for a graphical representation. First of all, I would like to explain about this graphical representation. It is what about? It is about the effect of frequency on what capacitance. This one is basically the capacitance. So I would like to explain first graphical representation, that is the relationship between what input applied frequency between 1 hertz to 1 megahertz and with respect to capacitance. So it can be clearly seen that from the graphical representation, when we have a lower input frequency, we have high capacitance. And as long as the frequency of input signal was varied from lower to higher, we will have lower capacitance. So there is basically the inverse relationship between applied AC signal with capacitance of my perovskite device. It was about first important explanation about CF analysis and about Nyquist criteria. About second graphical representation, we can see that it is basically the conductance. G is function of conductance. So we can see that we have exponentially increasing curve. It means what? It means that when we have lower frequency, we have lower conductance. And we can see that when we are having more and more higher frequency, like you can see that the range of 1 hertz to 1 megahertz, the conductance of the device was increasing exponentially. So there is a direct relationship between what? Between the conductance and between the input applied AC signal frequency. So there is an inverse relationship between the capacitance and applied frequency. Now I'm coming about third and most important plotation, that is about Nyquist plot. You can see that third graphical representation is basically Nyquist plotation. And I have just explained that what kind of explanation, what kind of graphical representation it has. It basically provide us effect of input AC signal on impedance of our perovskite or solar device in SCAPs only. And we can see that there are two range of axis, like x-axis and y-axis. So over here we can see that we have two kind of impedances. Z is denoted by impedance. Over here Z is denoted by impedance. On x-axis we can see that we have real impedance on x-axis, that is basically the positive part of the impedance of my perovskite device or solar device in SCAP. On y-axis, y plotation, we can clearly see that there is basically the imaginary part of the impedance. When we are going to compute a Nyquist plot, we will always have a same bell shape or rounded shape graphical representation. There will be two quantities, basically what the impedance, real impedance, and the imaginary impedance. The real impedance will be along x-axis and the imaginary impedance will be along y-axis, because imaginary impedance will have a negative value and the real impedance will have a positive. So we have a two criteria for positive impedance and for negative impedance. Positive part is being computed on x-axis, that is basically the real impedance, and the negative part of the impedance will be computed on y-axis, that is basically the imaginary. Now I am going to explain the effect of input AC signal on my real and imaginary impedance, and I will explain what kind of effect higher input frequency and lower input frequency can put on our impedance of perovskite device, or either on the real impedance, either on imaginary. So I am going to click just show, so that we can have some data in order to explain what kind of effect basically input frequency is providing upon our device impedance. So you can see that here is basically the range of input frequency. We can see that we have already set input frequency 1 hertz to range of what? 1 megahertz. So we have a range from 1 hertz to 1 megahertz, and I have already explained that EIS analysis or Nyquist plotation is basically the effect of input frequency signal over capacity or over impedance of my perovskite device. So we can see that when we have a lower input frequency, the capacitance was higher, and when it was frequency was varied from lower range to higher range, it can be seen that clearly that the capacitance was tend to decreasing. I have already explained this graphical representation that there is an inverse relationship between applied input frequency and the capacitance of my perovskite device. And when we talk about the conductance, this third column is basically for conductance. We can see that when we have lower frequency, we have lower conductance, and as long as the input signal of AC signal of applied frequency was increased, we are getting higher conductances value. It was same graphical representation. We can also get data from here, and we can get some plotation in Origin software and other software. So we have just computed that the first thing, the effect of the frequency on capacitance, we have seen that there is an inverse relationship, and we have seen that the effect of the frequency on conductance, we have direct relationship. Now I am coming towards the Nyquist plotation, that was about the computation of the effect of the input AC signal on impedance of my device. And we have two kind of impedances, like real and imaginary. And we can see that here we have a real part impedance and we have imaginary. I have just explained that we have two kind of impedances, positive impedance and negative impedance. In order to differentiate, we normally say that the real impedance is in positive value and the imaginary is basically in negative value. So we can see that over here, when we have lower frequency, we have higher impedance. We can see that we have higher impedance from over here. And then as long as we was increasing the input AC signal frequency, what was the impact on impedance of my perovskite device? You can see that on 1 megahertz, we have impedance, lower impedance 1.01. It is about the lower value. So we can see that as long as the input signal of AC signal of frequency is higher, more and more higher, and as was in changing with respect to lower value to higher value, we can see that the impedance of perovskite device was tend to decreasing. So higher the frequency, the lower will be the impedance of perovskite device. Like you can see that the real impedance. And when we talk about the imaginary part, we have already discussed that the imaginary part, the impedance value will be negative. That's why we have already plotted on y-axis. So what was the effect? We can see that from here we have higher, and then we tend to increasing. It means that the higher frequency range will also affect the imaginary part of the impedance. So we can simply collect some sample of set of range of frequency with respect to real and imaginary impedances, and we can put this computations or data in some other software, and we can clearly plot some graphical representation. And when we talk about the phase, we can see that phase angle is negative value. The effect of the frequency of lower, what we have minus 0.1543 value, and as long as the frequency was increasing, we can see that we are getting some dramatical representation like higher lower, and then we can see that on highest frequency input signal we have phase angle minus 7.19. So about the Nyquist plotation, we just need to remember that what kind of basic relationship it provides us. It is basically the graphical representation between what's the effect of the input AC signal with respect to impedance of our perovskite device. And we have already seen that there are two kind of impedances, real and imaginary. So in my today's lecture, I try to explain some important things that were about the Nyquist plotation, that was about the EIS analysis for perovskite solar devices in SCAP 1D, and I have explained that what is the effect of the set of range of input frequency on capacitance and conductance, and what is the effect of the input applied AC signal on impedance of my perovskite device. When we are going to simulate the Nyquist plotation, we will always have like same kind of curves like bell shape. Bell shape, it means what? It means that we have higher value of impedance of imaginary part on lower frequency, and it tend to decreasing, and after the range of higher frequency, we have seen that what kind of effect it has on the real part of my impedance. So the graphical representation, the effect of applied input frequency on impedance of perovskite device is basically Nyquist plot, and it is very helpful for those people who are trying to simulate the effect of the input AC signal on their impedance of the device. You can extract data from this computation, and you can put it into Origin software, and you can also get some smooth graphical representation. I hope this lecture will be very helpful for those people who are trying to compute the Nyquist plot, who are trying to set some testing values between the range of set of frequency and its effect on impedance of perovskite device for simulation part in SCAP 1D. Thank you for listening to me and supporting me. Take care, stay blessed. Allah Hafiz.